Breaking from intersecting branes.
So before I start, if Shimon is off the phone with Eliezer, I thought you called. Well, okay. Well, so I want to add to what I said last night, my congratulations to Shimon on this occasion. I have seen firsthand the amazing job he has done at Tel Aviv University, producing first-rate research, educating remarkable students, and keeping theoretical particle physics and string theory alive in my favorite city. So I'm certainly looking forward to many more years of talking to him about physics and all sorts of other issues. In fact, the subject of this talk was inspired by some conversations that Shimon and I had last year, and it actually goes back to 1997, where both Eliezer and Shimon and I, as well as other people here, were working on Hanani-Witten constructions of supersymmetric gauge theories, and we were all wondering what will happen if you break supersymmetry. And so I will tell you today some of what happens in some examples of this. Let me start with some sort of general comments just to orient you what sort of things I will be doing. And of course, we're very interested in what happens when supersymmetry is broken in string theory, and the kind of things that we're interested in are instabilities, perturbative or non-perturbative ones, what kind of backgrounds make sense. And in general, this is a hard problem, but one setup in which it's perhaps manageable is if you start with a supersymmetric closed string background and add to it a collection of branes that does not leave any unbroken supercharges, then it sort of feels like the supersymmetry breaking is more mild and you might hope to make more progress. And there are lots of examples of this that have been discussed in the literature. In some cases, a lot of progress was made. So I just listed here a few cases that most people here are probably familiar with. There is the work on non-BPS branes and brane, anti-brane systems in flat space-time that, of course, there was a lot of progress on in the last 10 years. There has been some work on branes propagating near Navier-Schwarz fivebranes, where, again, one can understand in classical string theory what these objects like to do. There has been some work on brane, anti-brane systems, where the branes and anti-branes wrap different cycles of Calabi-Yau manifolds. And more recently, there were brane models of chiral symmetry breaking, models that sort of have a relation to the dynamics of QCD that were discussed. And I am not going to discuss them here today, but there was a lot of interesting work that is still ongoing on those. Now, in this talk, what we're going to do is discuss another example of this type, which, as I mentioned, has to do with the Hanani-Witten construction. And one way to introduce this is to start with a certain supersymmetric gauge theory in 3+1 dimensions and embed it in string theory as a low-energy theory on branes. So I will say some words about the field theory later in this talk, but when you look at this field theory, what you see is that classically supersymmetry and gauge symmetry are broken in this theory, and non-perturbative quantum effects that were discovered by Affleck, Dine, and Zeiberg and other people restore both supersymmetry and the gauge symmetry. And the non-supersymmetric classical ground state, that state that breaks supersymmetry and gauge symmetry, turns out in the full theory to be an unstable but long-lived state in some particular region in parameter space where the classical analysis is valid. Now, when you go to string theory, the whole thing becomes richer. You can represent this gauge theory as a low-energy theory on some system of intersecting Navier-Schwarz and branes. And what we will see today is that in this string theory setup, you can see very similar phenomena to the ones that I just discussed just in a classical string theory analysis. So this is sort of standard in these situations where you embed gauge dynamics in string theory, where in some regime you have to do hard quantum gauge theory calculations, and in another regime the gauge theory analysis is not valid, but you can see very similar phenomena classically. This is basically the essence of the gauge theory gravity correspondence. And the other thing that we will learn in this particular system from this kind of analysis is that there are some surprising facts about the dynamics of the branes that are not apparent, perhaps, if you did not know the gauge theory results that are supposed to be valid. So let me start describing the system in more detail. As I mentioned, we're going to have Navier-Schwarz fivebranes and d-branes. And the dynamics we're going to be studying is 3 + 1 dimensional. So here are the 3 + 1 dimensions, the directions 0, 1, 2, and 3. And following some notation from 10 years ago, we will have two kinds of Navier-Schwarz branes. One kind that we will refer to as an NS brane that is stretched in the directions 4 and 5, in addition to those 4, and the NS prime branes that are stretched in the directions 8 and 9. So I also probably should say that in all the pictures that I'll draw from this point on, I will completely ignore both the direction 0, 1, 2, 3 in which the dynamics takes place, as well as all those of the 6 transverse directions that are not relevant for the analysis. So very soon you will not see anymore the actual space-time directions, but you should remember that they're always there and everything is stretched in them, and actually most of these directions as well. So what we're going to do is have sort of 3 stacks of these branes. One stack involves just NS branes, and I'm plotting here one of the directions in which they're stretched. And this direction is the x5 direction, which I will denote from now on by x, just not to carry around indices. So this is the x5 direction. The NS branes, of which there are k, are stretched in it, and the NS prime branes are at points, the points x1 and x2. And then there is a direction that I will denote from now on by y, which is a direction that on the previous transparency was called x6, which is transverse to all the branes. So they're at the point where they're localized in this direction. Now this system is, you can think of it as a sort of closed string background, because Navier-Schwarz fivebranes deform the geometry around them at string 3 level, and it preserves 8 supercharges. You can think about it as some sort of non-compact Calabi-Yau geometry, where we have some intersection that is localized in all 6 directions, and then some non-compact geometry around it. So this is what I say here. If you had just one kind of intersection, if these NS prime 2 branes were just not there, then this model where you have, let's say, NS prime branes sticking out of the board and one NS brane over here is just a T-dual description of a result conifold singularity on a non-compact Calabi-Yau. So here we sort of have 2 of them. And both of them are resolved with the resolution parameters related to these y1 and y2. And they're separated by some distance in one of the transverse directions. But again, this is a supersymmetric system. The only reason I'm mentioning this is that the kind of discussion we will have here presumably has some relevance for the study of non-supersymmetric branes on Calabi-Yau manifolds. Now, what we would like to do is add d-branes. So when we all worked on it 10 years ago, we did not have these guys. We had one such intersection, and this was dual to n = 1 super Yang-Mills with gauge group in this notation SUN1. And a lot of mileage was made out of it. People got some interesting non-perturbative results about gauge theory from this setup. And now we would like to break supersymmetry. So what's the simplest way to do this? Is to have two of those. That's why I had those two kinds of NS prime branes separated in space, and have two of these n=1 Yang-Mills theories, but that preserve different halves of the supersymmetry. So this one preserves one n=4 supersymmetry algebra in 4 dimensions. This one preserves an orthogonal one, and together they break all supersymmetry. So this is a setup in which all supersymmetry is broken. This is a solution to classical string theory. And, but the thing that breaks the supersymmetry is, as I mentioned earlier, just the branes. And so what we would like to do is understand what this setup does. This is, of course, not guaranteed to be any kind of ground state. This is, as Eliezer likes to say, our starting offer. But you know, maybe some higher bids will arise at some point, and so we will have to analyze what they are. Now, what kind of dynamics would you associate with it? Well, it's sort of 0th order. As I said, you would just say we have a UN1 super Yang-Mills here, a UN2 n=1 super Yang-Mills here, and if the distance delta x is large enough, they don't talk to each other. So that sounds boring. What does break supersymmetry here? Well, what breaks supersymmetry, one way of saying it, is a bifundamental scalar field corresponding to a fundamental string stretched between these two intersections, right? So there is a fundamental string stretched here that does not fall into any kind of supermultiplet. So that's one way in sort of field theory language to see that supersymmetry is broken here. So we have n=1 super Yang-Mills with gauge group UN1 cross UN2. And we have, in addition to all the fields in the supermultiplet, this tachyon. Now, of course, the tachyon is, in principle, not tachyonic. It's actually very massive if the separation is large. And therefore, you might think that it's not interesting. At low energies, you just have this UN1 cross UN2 theory, plus some very massive field that you will never see. And so that's the low energy system here. It's just supersymmetric in Mills theory. But in fact, this is not true, as we will see very soon, just based on totally elementary considerations. The truth is that while this tachyon is very, very heavy, if these two intersections are well separated, in some regions in parameter space, it is important to take it into account because it could condense by a lot and thereby lower the energy of the system. So the backgrounds this background we started with can actually tunnel somewhere else. And as I say here, it's obvious already at the simplest level of discussion here, where you just think of this whole picture that I've been drawing there as taking place in flat space, and treating the fivebranes as surfaces on which the d-branes can end. Because that configuration that I was drawing, in which we had branes going this way and anti-branes going the other way, can in principle be continuously deformed to this one. Right? The branes can sort of come together by deforming this way and then reconnect and shoot up into something like this. Now, of course, two things are immediately obvious from these pictures. One is that if this happens, the gauge symmetry is broken. So I will refer to this as the broken brane configuration. The original UN1 cross UN2 gauge symmetry of that intersecting brane system here is broken to the diagonal UN1 times some residual symmetry from here. And the other thing that is obvious is that if this happens at this level of approximation, this is, well, on the way, even if the energy of this guy is somehow lower than the energy of just the straight brane configuration, on the way between the two, the energy first goes up and then down. So it's the potential sort of has this shape where the original configuration that we started with, this one, is locally stable to perturbations where the ends here move. And if it's unstable, it's only to some kind of tunneling. Now, well, what is the energetics here? Again, at this level of approximation, it's completely elementary. You just have to calculate the difference in energies between the broken and unbroken brane configurations. And you find that if the separation is sufficiently large, this is positive. So that's very reasonable. If these two intersections are very far apart, the branes want to go down and then up. They don't want to go between the two NS prime branes. And more precisely, this is the criterion. So if this inequality holds, the ground state of the system, at least in this approximation, is the one we started with, the unbroken configuration. And if this inequality is not valid, if the two are sufficiently close, then, of course, it's the other way around. Then the gauge symmetry is going to be broken, and the true ground state of the system, just in this classical approximation, is going to be this one. Now, so here are a couple of additional useful things to note. One is that I didn't even bother to mention this, but both of these brane configurations break supersymmetry, no matter which one has lower energy. But we will actually argue later on that the true vacuum of the system is supersymmetric. It's never one of those two, but this will rely on quantum effects. And the other one is this point that I already made, that even the configuration that has higher energy in a given regime can only decay by tunneling because they are local minima of the effective potential. And we will see that, in fact, there are some interesting changes to this picture that I just finished presenting when all sorts of quantum effects, classical string effects are taken into account. So perhaps let me pause here and ask for any questions about this setup before I move on to what I actually want to say about it. All right, so, well, what kind of corrections do you... Sorry.
What about the U-shaped configuration?
Well, so, as I said, this whole picture is done in a flat space approximation. And in fact, in flat space, things go in straight lines between any 2 points. But indeed, the corrections I have in mind, which I'm about to introduce, have to do with your question, namely the fact that these NS branes attract any D branes like that. And as you're familiar with, what the D branes will do in response is curve. So we're about to actually get there. Now, well, so that's what I say here. The D branes actually don't live in flat space. They live in the gravitational potential of the NS branes. And it's pretty easy to analyze this problem of what happens to the D branes in the gravitational potential of the NS branes. You just replace the NS branes by their geometry, which is the famous Cullen, Harvey, and Strominger geometry, which I wrote here. Everything is determined by the harmonic function of the fivebranes, and I would particularly note this characteristic distance scale L here, which is proportional to the string scale, but also to the square root of the number of fivebranes. So a useful thing to remember about this is that if we have many of these NS branes, then this characteristic length scale is very large. And the other thing that I should mention is that this is, of course, a supergravity result. And so in addition, so it's valid, it's a good approximation to what happens in the full string theory in 2 limits. One is when this k is very large, so that all the distance scales involved are large. And the other is if r is very large. If you're just discussing dynamics at very large distances, even for L of order L string, then the supergravity approximation is going to be useful. And we will actually use it in this regime later on. All right, so that was the five-brane background. It's familiar to a lot of people here how to describe d-branes in this background. You just write the dBi action for the branes and ask for solutions, which, as Kobe just mentioned, are smooth curves which go between the 2 points where the ns prime branes are, and in between satisfy the equations of motion for d-branes in this ns5 brane geometry, which I wrote the relevant action here. So it's a pretty straightforward exercise, and of course, even without doing the calculation, you know that the qualitative solution will take this sort of U-shaped form just because of the attraction. And basically, the important thing to know here is not so much the exact shape, but how low the d-branes will bend in the ns brane geometry. This is the analog of, say, this U0 in D4, D8 system some people here are familiar with. And so I'm going to say a few words about this solution without actually solving the equations. Of course, everything here depends on the parameters of this brane configuration, which are the separation in x and the height in the y direction, as well as this k. And for simplicity, I'm going to just describe the results when the y's are the same of the two. It's very easy to do it more generally, and the results are not that different. Yes, Michael?
The approximations k is very large, but n1 and n2 are fine.
Yeah, n1 and n2 are anything. They could too. And k does not have to be very large either. That's actually, I sort of alluded to it briefly, but let me say it again. So you see so if k is of order 1, then when you get to the natural scale at which the ns branes curve the geometry, that scale is of order the string scale, and stringy effects are in principle important, although there are known examples precisely in this problem where actually a dBi analysis gives exact results. But an important fact for us later is that even if k is 1, this formula is supposed to be correct if you are at sufficiently large R. So if you look back at this geometry that I was drawing, so imagine, I mean, intuitively, again, without even solving the equations, you know that if y1 and y2 are enormous, and delta x is enormous as well on the string scale, presumably this whole shape will sit in the region of large y, in which this dBi approximation is actually valid. So that's the other regime I was mentioning, in which you don't have to worry about string corrections to the Cullen-Harvey and Strominger result.
If k is of order 1, why do you take into account the symmetry between k and s branes and not with the other?
Yeah, so, well, wait, there's no way I will remember both of them, so let me answer this one. I don't want to embarrass myself in my early stage Alzheimer's. The reason for that is, so first of all, it is true that this is an approximation, and the question is, why do I think that it's a good one? And the answer to this question is that the basic dynamics that we're trying to capture here is the dynamics of this process, of the process where the ends of these guys come together. In fact, as you know very well, a better way of thinking about it in precisely that geometry that we're doing is that really what the ns branes are doing is going down here, proceeding along the ns brane. Maybe I said it wrong. What the d branes are doing is they're going down here, proceeding along the ns branes and going up. So they can just continuously deform up, right? I mean, this part of them is sort of massless because the tension of the branes goes to 0 here. And so they can deform up. And this is the basic dynamics that we're trying to capture here. The dynamics of the process where you go, this happens and you go to something like this, right? And that dynamics clearly has to do with the region near the NS branes. If you sit on one of these NS prime branes, all you see is that the D branes, they started out like this, and they, imagine again that all the distances that are involved here are very, very large on the string scale. So, you sit on the NS prime brane, and it starts out actually not like this picture, but like this one. And, so they curve a little bit. So all you see when sitting on the NS prime brane is it sort of curves a little bit that way. It changes direction a little bit. And all the fun goes on here. And that is why, for K of order 1, I believe it is a good approximation to focus on the effect of the NS branes while ignoring the one of the NS prime branes. Okay, now question number 2.
Right. I assume we will discuss it later, if not, should answer now. The D branes are going to curve the NS prime.
Yes?
And they point in a different direction.
Yes.
Does that change the...
No. I am actually not going to discuss it later just because of lack of time. But, since I'm not planning to discuss it, let me comment on it right now. The way to think about the system is as one where you have some dynamics going on near an intersection, and it's coupled to all sorts of modes that live in the bulk. So it's intuitively clear, and there are lots of examples of this sort that we're familiar with, starting with just D branes in flat space that intersect like that, where there is a tachyon at the intersection, and then the tachyon condenses and they reconnect in some way, going through the non-supersymmetric orbitals with localized tachyons at the tip. We know what happens in the systems. What happens in the systems is that whatever needs to happen at the intersection happens. If there's an instability at the intersection, then the instability gets resolved in some way. And then, at some point, these NS prime branes suddenly realize, and this could be a light year later, that, oops, something happened here. Right? So again, think about the process I just referred to in answering question number 1. Imagine that these Y's are enormous, and what really happened was that some instability took this straight brane configuration to that U-shaped one. But what really happened as a real-time process, right? As I mentioned before, these things started sort of moving up here. And when they did that, this guy didn't know because he is a light year away. And then after a year, the fact that something happened there all of a sudden reaches this, and then he has to react somehow. Well, how does he react? A pulse of sort of the scalar field that represents this bending starts propagating towards infinity on it. And of course, it takes this pulse an infinite amount of time to make its way to infinity. But this is of no interest to somebody who is living at the intersection. As far as they're concerned, it's after a millisecond, everything has rearranged. And again, there's nothing here that is different from the other examples I mentioned, like the APS work on non-supersymmetric orbitals with tachyons, or even this textbook example straight from Polchinski. So what I'm saying is that you don't have to worry about this. You have to analyze what goes on at the intersection, and then these guys will take care of themselves. Which is why I'm not going to discuss this part of the problem. Right, so as I said, I was in the process of telling you that the solution of this equation in principle depends on all these parameters, like the delta x and the y's, etc. And I'm going to tell you a little bit about what the solution looks like in the particular case where the two are at the same height, just so that I don't have to take into account the dependence on the one extra parameter. But it's basically the same thing when you generalize. to the more general case. I'm not going to discuss most of the equations. The basic starting point of this analysis is that you can derive a relation between the separation of these NS prime branes, their mutual height, this characteristic scale L, and the minimal value of the height that they reach. And what's interesting is that you find that there are two distinct regimes in this analysis. The one where the branes are sufficiently low relative to the NS branes, and the one where sufficiently high. So the case that we are sort of interested in, the case in which supergravity is valid, is the case where this Y is very, very large, where the NS prime branes are very far from the NS branes. And I'll get to it second, but first I wanted to discuss what happens in this case, which is kind of interesting.
Question?
Yeah.
The field theory limit is when y, the DNS2 goes to, the distance goes to 0 to the other one?
Well, I'll comment on it a little bit before, but no, you don't have to take any such limit. So when I said that, this brane configuration that we started with is described in the infrared by this gauge theory, UN1 cross UN2 gauge theory, with n equal 1 super Yang-Mills, I did not mean to say that this is only somehow true in some limit. The statement, of course, is that this gauge theory description is valid for arbitrarily large y's and delta x and all of that. And, of course, there's always the question of what is low energy. How low does the energy need to be in order for this field theory description to be valid? And we know the answer to that. It involves the string scales, the Kaluza-Klein scales, etc. So, obviously, the larger this y is, the smaller the energies are for which the gauge theory description is valid. You have to be below all the possible Kaluza-Klein scales. But you don't have to take any limits. So let me start by describing what happens when this y, the joint height of the two NS prime branes, is sufficiently small. So y less than L, of course, means that the NS prime branes are already in the region in space which is heavily influenced by the non-trivial geometry of the NS branes. And so your flat space intuition could fail there, and indeed it does fail, although I stress that this L could be enormous because the number of NS branes that create the geometry could be enormous. So what you actually find when you do this analysis is that if the distance between the two NS prime branes, this delta x, is smaller than pi times L, then it is not even true that this configuration is a local minimum of the effective potential. In other words, the deformation in which they sort of rise up and turn into this U shape is one that continuously lowers the energy. So, in the flat space approximation, we saw that it's always a local minimum, because if you try to move them up, you have to raise the energy. But in this curved geometry of the NS branes, it's just not true. It actually looks like this. There is a unique minimum of the effective potential that corresponds to this smooth solution. And then, of course, if you try to deform the smooth solution into either directions, you find that the energy increases. Now, of course, the other question is, well, what happens when you keep this y fixed, and you change the separation, this delta x, which you can think of as some sort of mass parameter, or for example, the mass of the tachyon field. And what happens is something very reasonable. As you take delta x to 0, as these 2 points come together, it's intuitively obvious and indeed true that this curved shape just goes straight. It looks sort of like that. That's obvious because it doesn't have a chance to curve in the geometry. And on the other hand, as you increase it, as delta x approaches pi L from below, this U shape sort of goes down farther and farther until it just becomes this. at delta x equals to pi L. And then it continues looking like that for any larger delta x. So to say it in a different way, for delta x larger than pi L, there just isn't a smooth curved solution like this, and the only solution that exists is this one. So as you increase delta x, this minimum sort of moves this way and finally hits the origin and becomes like that. So this is what you find, and there's actually a slightly useful way of thinking about that, about why it is that the straight brane configuration is actually a local maximum of the potential and not a local minimum, which has to do with the properties of fundamental strings stretched between the branes and anti-branes. I told you before that in the flat space approximation, a string that stretches between the two, the d-branes and anti-d-branes here, is massive if it's sufficiently long. And certainly, when L is much larger than L string, you would think that it's massive. But in fact, this is not true. In fact, what happens, because of the curved geometry of the fivebranes, this string develops a sort of localized instability in the throat. You can check that its mass is given by a formula like this. It's actually a open string analog of what Nati, Sunny, and I did for closed strings, like this mode on the circle that becomes tachyonic when we change the radius of the circle of the fivebranes. There you get a very, very similar looking formula. But this is a very simple way of understanding why, when these d-branes are sufficiently close here, this configuration is the maximum. This tachyon sort of wants to condense. And so you can describe what I said before by saying that this system in this regime, when the NS prime branes are sufficiently close to the NS branes, exhibits a second-order phase transition at delta x equals to pi L. The order parameter can be thought of as the expectation value of this bifundamental tachyon, and it has the property that for sufficiently small delta x it's non-zero. It approaches smoothly the value 0 as delta x goes to pi L and then just stays there. And of course, the two phases are qualitatively very different. When the tachyon is condensed, the gauge symmetry is broken. And when its expectation value is 0, you have the full UN1 cross UN2 gauge symmetry in the system. And the transition between the two regimes happens as a function of this mass parameter, delta x. Now, another way to this, sorry.
They just meet each other?
Yeah. So the tachyon is in a sense a property of this configuration, and its condensation leads you to this one. And I don't want to be sort of very mystical here. This is not any different from the geometric analysis with the dBi action that I did, but it's just a convenient way of thinking about the difference between the broken and unbroken phase because this tachyon is charged under the two gauge groups.
Can you put it up in some way into the dBi and get...
Yeah, that's actually a very good question. In fact, it's a question that we all discussed in the common room at the Weizmann Institute in the context of the D48 system. And it's exactly the same issue here. As you know, we don't quite know how to do that. But here I don't need this detailed knowledge. Incidentally, this is also related to the open string analog of the FZZ correspondence, which is in this context the statement that this U-shaped curve for the D-brane has automatically, in addition to its curved shape, this tachyon turned on, just like on the cigar that Eliezer always likes to remind me was discovered by him, Shmuel, and Forge. In addition to the geometry that Eliezer, Shmuel, and Forge discovered, there's also a winding mode condensate that at that point was not known. the cucumber, okay? The semi-infinite cucumber. Do you actually use that name in the paper? Okay. I think you used it in our discussions. Yeah, so this is the picture you get in this regime. And I guess the last thing I want to say about this regime is to plot the energetics of the branes in a way that Amit actually suggested to do it, which the reason I'm doing it here is that I want to avoid the whole analysis I just described for the other case where this y is large, and just plot for the other case this picture. So that will save us time. But in order to do this, we have to understand how this picture relates to what we just said about this current case. So first of all, ignore this green line here. And the black lines are precisely what I just described. So we plot the sort of energetics as a function of delta x. And what we described here is the situation where the ground state for delta x smaller than pi L is this U shape. And the other one, the straight brane configuration, does not exist as even a local minimum of the effective action, which is why there's only one curve here. Then, as delta x approaches pi L, this U shape sort of continuously approaches the straight brane configuration. And at delta x larger than pi L, all that exists is the straight brane configuration, which therefore is the minimum of the effective potential. So this is just another way of describing what I already told you.
In the starting point, when they go like that, let me bring them close. Is it an arbitrary function or is it interpolation free? In other words, does the potential for this curve, is this a solution of the equation?
No. Yeah. Well, sorry. So the facts. So as I just described, the facts are the following: if they are sufficiently close, if this delta x is smaller than pi L. And actually, I should stress, I mean, it's probably obvious to you, but perhaps I should stress to others that I'm doing here this case, but the case that Nati and other people studied in the context of the ISS model, where one of these NS prime branes is replaced by a stack of D6 branes, is exactly the same for the purposes of this discussion. So, yeah, so the So the facts are the following. Again, this configuration is a solution of the equations of motion, but it's a local maximum. It's a saddle point. There's a direction in which you can continuously decrease the energy, and that direction is the direction in which it sort of goes up here continuously.
And that's for arbitrarily large delta x?
That's for arbitrarily large delta x, smaller than pi L, which could also be arbitrarily large. I mean, of course, if L is, so remember, L is L string times square root of k. So for fixed k, for fixed number of these NS branes, L is fixed, and then this is the bound on delta x in which the statement I'm making right now.
If delta x is bigger than that.
Okay, if delta x is bigger than that, then there is no solution like that. Then there is, but there's just no solution to the dBi equations of motion that looks like that. There's one solution to the dBi equations of motion, which is this one. And again, the way these two are related is that as you increase delta x towards pi L, this thing just moves to the left, and at delta x equal to pi L, they collide, the minimum and the maximum. So there are no barriers here. Perfect. And again, all of this, I stress, is when this y parameter is sufficiently small. Now, I anticipated indeed that Louise here will tell me that I don't have enough time to repeat everything I said for the other case, and therefore all I put here on the slides is the analogous picture to the one I had previously for large y. So this is the case where imagine that the distance between the two kinds of NS branes is arbitrarily large, let's say, in string units. And what happens then? Well, again, ignore the green line. The analysis I described before gives something like this. First, for sufficiently small delta x, you have, again, this U-shaped solution we were discussing. and the straight one is not a minimum. It's a local maximum for exactly the same reason. There's a tachyon on it. So there's a unique thing here. Then as delta x becomes larger than pi L, the straight brane configuration becomes a local minimum of the effective action, and this is what I draw here. But it's only a local minimum. Its energy is still much, much larger in general than the energy of this U shape. So there is a large regime for large Y where both of them exist, and either one or the other is the actual minimum of the potential. So both of them are local minima. This is the only things I draw here, local minima of the effective potential. But in this regime, it's this U shape, which is the global minimum, and in this one, it is the other one. And one further interesting thing is that the flat space picture would lead you to believe that no matter how far you separate these two NS prime branes, this U shape remains a local minimum. It might be metastable as opposed to stable, but it's still a local minimum. And this is in fact not true. What you actually get from the dBi equations of motion is that at some finite value of this mass parameter delta x, this metastable state just ceases to exist. It goes out of the spectrum. And of course, the straight brane configuration that just go down remains for arbitrarily large delta x. So this is a picture in which we have a first order phase transition. For small delta x, the global minimum is this U shape, and the tachyon is condensed, the gauge symmetry is broken. And then at some finite value, which you can easily calculate, I didn't put the formula here as a function of the parameters, the system undergoes a first order phase transition to the unbroken phase, where the full UN1 cross UN2 symmetry is unbroken. And so this concludes the classical part of this story, but in fact there are some interesting quantum effects here. So far I described for you the classical dynamics of the branes, and in fact there are interesting modifications that have to be there when you turn on G-string effects. And to see that, I will show you that this is certainly the case for small separation of the branes. And this is something that is easiest to see in the following way. So if you just take the separation of the NS prime branes to 0, you arrive at a configuration like this, which is very familiar to people who studied these Hanani-Witten models 10 years ago. This is, of course, a supersymmetric model. It's a supersymmetric gauge theory with this gauge group and matter in certain bifundamental and adjoint representations of UN2. So the bifundamentals, as usual, are strings that go like this, and the adjoints are strings that connect these D branes here. And there is an interesting superpotential. There is a cubic superpotential for the adjoint and the bifundamentals. This is related to the fact that this model is the Zyberg dual of some other brane configuration that I will draw in a moment. And this separation, which is set to 0 in the picture on the previous slide, is described by a linear superpotential, as explained by various people, including Nati here, in this way. So this mu is 0 when you're in this configuration, and it's not 0 if you displace, as we did for most of our discussion, the two NS prime branes in the x direction. Now, this gauge theory description is, of course, only good for small separations, for small delta x. And in that regime, you can use the gauge theory to analyze the full dynamics of the brane. So this is related to your question before. No matter how large these y's, etc., are, if you're interested in sufficiently low energy dynamics, you can do it in gauge theory. And in this particular analysis, what's important is that this delta x, or the mu parameter, is sufficiently small. And sufficiently small is actually very, very small here. But when it is sufficiently small, you can just use the standard techniques, the sort of techniques that Nati used 10 years ago or more, to analyze supersymmetric gauge theories to show that there's a quantum superpotential that restores supersymmetry. And the classical non-supersymmetric vacuum states that we have been discussing this whole hour are actually, in this regime at least, small delta x, not stable. They are long-lived excited states. And so this takes us back then to ask, well, what happens in general? So I reproduced here the picture I had in one of the previous slides. And what we learned now from the gauge theory analysis is that at least at very, very small delta x over here somewhere, it is not true that the classical ground state is the true ground state. We found that there is a state which is supersymmetric and slightly lower energy from it. And then we can ask, well, what happens if you try to extend this to larger delta x? The green line is representing our expectation that there's always a supersymmetric ground state. It's lower energy than both of the states I discussed previously in this talk. It is the true ground state. And then there is this interesting pattern of excited metastable states above it. And as I indicated here, this true ground state becomes very, very similar to the metastable state at small delta x, but it also becomes very, very similar to them at large delta x, at large separation of the branes. And one way to see this is that this system is supposed to be already in sort of string theory related to, by Seiberg duality, to a brane configuration like this, which in the literature from 10 years ago would be called the electric configuration, whereas the one I've just talked about would be called the magnetic one. So there is a general expectation that I don't think we are sure of, but you might entertain, that the low energy limit of this brane configuration is exactly the same as the low energy limit of this one for all values of the parameters. I don't know whether it's true or not, but if it's true, then it's very clear in this description what the supersymmetric ground state is. It's simply this. This is what happens in the electric theory when you separate these NS prime branes, and this should be the supersymmetric vacuum. And so the reason I'm saying that the true supersymmetric ground state approaches this metastable state at very large separations, very large masses, is that basically there is not much difference in the low energy dynamics between this configuration and the one in which this is reflected upwards if the separation of the branes is very large. So this is the picture that we end up with. Classical dynamics with all sorts of interesting effects and some supersymmetric ground state that is difficult to see in this language. The one comment I'd like to make before I end, out of all the comments I wanted to make, which is actually interesting for the purposes that you guys were interested in the system in the first place, is that, of course, in some region, this problem reduces to the gauge theory phenomena studied by intrigator Seiberg and Shi that Nati reviewed here today. I mean, not today, yesterday. But what's interesting is that just like one typically finds in the systems, there is another regime in which you see essentially the same phenomena just in classical string theory. And when I say that, what I mean is the following. If you look at the picture we have in the regime where all the distances are very, very large, and you look at just this part of the picture, so what do you see? You see a supersymmetric ground state, which is almost the same as this non-supersymmetric state, which you see classically. You see a metastable state, which is a continuation of the metastable state that you discussed in your papers to this regime. And you see that as you increase delta x, which is that mass parameter that appears in ISS, at some point, this metastable state disappears. But in ISS, this phenomenon was difficult to see, this point, because this was a place in which neither the weakly coupled electric nor the weakly coupled magnetic description was easy to analyze. Well, neither the electric or magnetic descriptions were easy to analyze. Whereas in this regime, in the parameter space of the brane configuration, it is easy to analyze. It's just a classical string theory effect that if you try to stretch this U-shaped D-brane between two NS prime branes that are very, very far, just classical gravity tells you that you cannot do it. But so the basic message of this is that, like other examples of gauge gravity duality, this is a situation where you can see very similar phenomena to the ones you're familiar with in gauge theory using branes. Thank you.
Thank you. Tom?
You're not saying that an actual field theory place where the metastable state disappears is dual to the gravity system.
No, well, I'm saying that it works like it always does. That in a situation, so a good example of what I have in mind is Witten pointed out that D4 branes on the circle twisted boundary conditions have something to do with Young-Mills. But the place in which you can analyze that system using classical gravity is, of course, a place in the configuration space of D branes where the dynamics has nothing to do with Young-Mills. It's the same here.
Nothing.
I still don't understand the answer to my question. I understand if you have a solution of classical equation of motion, as a tachyon, not as a solid, you roll to wherever it was.
Yes.
But when I don't have a tachyon, it's metastable, it's not completely clear to me when we should and when we should not explore large field excursions which change
Yeah.
the asymptotic behavior of the brain.
Okay, so the answer to... Right. So the answer, so in some range, I mean, again, I didn't have time to discuss all of this here, but there's a very simple way, you taught me not to overcomplicate things, right, a long time ago. And there's no reason to overcomplicate this either. You can go to a region in the parameter space of this brane configuration where everything to do with this tunneling takes place over here. And the NS primes branes are next to that galaxy that Tom recommends that we look at before it disappears. This tunneling business is just some statement that you have to wait a long time before things happen over here. But once the thing tunnels over here, it still will take a long, long time before the... No, because this business with the different asymptotic behavior has something to do with over here. They're basically almost not coupled to those scalar fields. Well, I think... Yeah, it's exactly the same. Yeah, that was one of. Yeah.